Great, thanks. So we've seen some great talks on foundational algorithms, but today I'm going to present a tool to automate computation of a powerful algorithm for developing robotic models. Okay, so first I'm going to cover how you mathematically take dynamics on manifolds. Then I'll cover a computational framework that we built to automate this procedure. And then I'll get into the scope of this tool, what systems can we build models for, what robotic systems can be inspired by these models. Okay, so some motivation for this work. We have two mechanically identical quadrotors. The one on the left is parameterized by Euler angles, and there's a load that's hanging from it on a string. And there's two scalar angles which describe its position with respect to the quadrotor. Where on the right-hand side, I'm going to just describe the configuration manifold as a Cartesian product of the reals, which the quadrotor and the load exist on. And then I'm going to define a spherical manifold, S2, which constrains the load with respect to the quadrotor. And orientation of the quadrotor is going to lie on the special orthogonal group. Okay, so you can see two different types of equations of motion. On the left, those dynamics are fully encapsulated by this red boxed equation. So on the right, we're getting these succinct, singularity-free, and globally valid dynamics. Okay, so this kind of offers, in some sense, a nicer paradigm in which you can construct control architectures for these robotic systems. So that's kind of the motivation for building models directly on its configuration manifold. Okay, I want to get into another kind of case example. So here's a planar pendulum, double pendulum. So we have theta 1 and theta 2 swinging like this. The model's pretty simple, pretty straightforward, but things start to get complicated if I make the joints spherical. So you can see like these blue and red are example trajectories from when I simulated the system, so it can come out of the plane. Here's the new dynamic model, and it jumps in complexity pretty quickly. If you want to start kind of adding more mechanical degrees of freedom to the system, you're going to start to get equations where you need to squint more than you already have to see these equations. And you start to lose a sense of kind of mechanical intuition for what happens when you start to embed more complexity in your mechanism. At the end of the talk, I'll show the same model for an identical system that's much more succinct and I think much more intuitive. Okay, so now I'll talk about the mathematical algorithm for computing dynamics on manifolds. So we're going to use variational calculus. We're going to borrow the Lagrange to D'Alembert principle. So we need the Lagrangian of our system and the infinitesimal work. And from this, we can construct an action integral between 2 points on our configuration manifold. And with this, we can define the least action path. And in a variational context, this means that for very small paths, we can understand our second order, build a second order differential equation for the dynamics. Okay, so this is kind of the math slide for the talk. I'd like to run through an example computation. So here we have a pendulum bob that exists on the sphere S2. Q is a unit vector which points to the location of this bob. So we have the variations kind of explicitly written in the bottom left of the slide. So we have a delta Q. This is described as general vector Z crossed with Q. So this generalized vector would exist on a tangent plane that intersects the sphere at the location of the pendulum bob. Okay, and the cross product of this with Q kind of gives me my variation to make sure that this pendulum bob isn't moving radially, it's kind of restricted to the sphere, okay? So I'll walk through this computation. So we're going to take the variation of the action integral and set it to 0. Now in step 2, we're going to apply this variation inside the action integral. In step 3, we substitute this variational knowledge of how our dynamics evolve on the manifold into the action integral. Now we're going to collect with respect to this generalized vector. Now we kind of have terms in this generalized vector z and its derivative, so we want to get everything in just terms of z. So we perform integration by parts on those terms in our dynamics. And finally, we're able to collect everything with respect to this generalized vector. Now a trivial solution to this integral is if I just set the generalized vector to 0, but this is not possible because it's a magnitudinal vector which exists on the tangent plane. So what I can do is, because this is, I can set the right-hand side of the dot product to 0, and in a variational context of this integral, then that gives me the information for my second order differential equation at any point on the manifold, okay? So with a simple algebraic manipulation, I can arrive at these succinct equations that you see in step 7, okay? So now we want to automate this procedure. So we took a look at what tools are available. You have things like Atoms, sim mechanics, Maple Sims. These are great if you want to plug and play with different models, simulate them forward, see how different things evolve for various models. But each requires a scalar parameterization of your configuration space. So it's quite simply not possible for us to use this for implementation of our algorithm. We need to know exactly how the dynamics are evolving on these special configuration manifolds. Okay, so automation requirements for our tool are that we need to know things like Q is restricted to the sphere, rotation matrices R are restricted to the special orthogonal group. So things like the inverse of R is the same as its transpose. And things like the scalar triple product will allow us to collect with respect to certain vectors in the reals. Okay, and I would have loved to do this in something like MATLAB or Mathematica, but unfortunately, if I want to have something like a rotation matrix R, it's subcast to 9 individual scalar symbolic variables. So I'm not able to just have one symbolic element R, which kind of captures the properties of the special orthogonal group. Okay, so now I'll get into how we implemented this in a software framework. Okay, so we're going to use Scala, which is a functional object-oriented programming language. This allows me to treat different mathematical elements in a case-by-case basis. So for example, differentiation of constant vectors and unit vectors evolves differently. So I can treat them how they're supposed to mathematically compute. Our data structures will be abstract syntax trees, which I'll get into in a minute. And then I'll go into some of the key steps for implementing the computation. So here is a class hierarchy. This is pretty dense, but I can just say that in the green we have scalars, in the blue we have these symbolic vectors, and in the red we have these symbolic matrices. And there's 2 different types of nodes that can exist in the abstract syntax tree. We have parent nodes, which can basically add things together or perform matrix multiplications, perform operations on different nodes. And then we have elemental nodes, which would kind of be the different mathematical properties, such as you can have constant vectors, you can have skew symmetric matrices like an inertia matrix, or you can have various other things like unit vectors if you want your configuration space to evolve on the sphere. Okay, so this is how we kind of bring all these different nodes together. These are called abstract syntax trees. So it's pretty straightforward. So I'd have like an add node that can, for example, the Lagrangian, I can combine my kinematic and potential energy like such. And then these multiplication parent nodes can just bring the rest of my terms together. Okay, so here's an example of a step that we need to implement in the procedure. So we need to take the variation of the action integral. So you can see in the red, I'm kind of focusing on these subtrees. So I can take the variation of the dot product of Q dot with itself, and I apply the chain rule to get the following. And then in substitution, I can start to include the knowledge of how my dynamics evolve on the manifold. So for delta Q dot, I can substitute the chain rule of this generalized vector crossed with Q. Now I want to start collecting, again, as I was saying earlier, with respect to the generalized vector. So using the scalar triple product, I can kind of rearrange vectors in my data structure. Okay, and then differentiation, which is kind of similar to variation, but this will allow me to do things like integration by parts to get everything in terms of the generalized vector. And these kind of consist of the main functions that I need to run the whole computation. So there's other things that simplifying relationships that I can use to reduce the complexity of the data structure. So for example, if I have R, which would exist on the special orthogonal group, if I happen to parse that I have a transpose multiplied by itself, then I can take that as the identity. So simplifications like that allow me to reduce the complexity of the data structure and arrive at the dynamical solution. Okay, so now I'll get into kind of validation of our procedure. So we have some example systems here. On the left, we have the spherical pendulums, and on the right, we have the rigid body counterparts. The bottom left dynamics of motion correlate to that example I showed earlier with the blue and red trajectories for the double spherical pendulum. What you can see here is a much more compact form of the equations. And I think that you can start to get a sense of how different degrees of freedom in the system interact with various mechanical properties of how you would possibly design such a system. So I think this is in many ways a favorable form to pose your dynamical model. Okay, and to touch on the alternative approach briefly, right now this is the first tool to do this procedure. So your other option is to do the hand computation. And for example, if you want to do this for a quad rotor, it's going to be quite a few pages long. It's prone to error. We do this in the lab. It's kind of a pain in the butt. So having an automation procedure is nice to have. Thank you. And these are some kind of more realistic robotic systems that we were able to automate the dynamics for. So on the left, you have your 3-link walker, the stance and the flight dynamics. In the top right, we have a quad rotor with suspended load. And in the bottom right, we have a reaction mass pendulum. Okay, so basically, the reaction mass pendulum is something that can give you kind of a higher fidelity rotational dynamics for a walking mechanism as it's in its flight stage. So these are some models that we can get these compact dynamics for and start to build nice control architectures for these types of platforms. So a dirty laundry slide for this work. Our computable manifolds for this procedure are the reals S2 and SO3. We can't compute right now on manifolds S1 and SO2, and these are very common. This is like a rotational joint for a motor. This is because we need some type of scalar parametrization to describe its embedding in the real space. So future work might be finding a way to possibly describe our Lagrangian with these types of degrees of freedom. We're also interested in continuum mechanics. So for example, I could have an infinite chain of spherical pendulums and describe the dynamics of that. And another, I didn't talk about this, but the last item on the dirty laundry is we can't simulate the computed EOMs and the differential equations that we compute. So we're going to look into discrete mechanics, which will allow us to, we'd like to automatically compute kind of the next step that you would put into an integrator. And we're excited about this because potentially we could go from just having a Lagrangian of your system to having a simulatable form of the dynamics. And this would be kind of the ideal framework for kind of just at a design level, designing new configuration spaces for robots that might be particularly ideal. So thank you for your time, and I'd love to take any questions.
Alberto is our first responder.
You sort of hint on it on this slide, but I wanted to ask you if you can go back and tell us a little bit of where should we use this, or what are the conditions under which it makes sense to use this versus, my question was going to be if I can use this to simulate the system. Right. But if I cannot use it, then what do I use it for?
Yeah, thank you. That's a great question. A reason that you would be interested in this type of paradigm for modeling your system is there are a lot of kind of issues that come if you parameterize your system with these scalar local variables. I tried to talk about it a little bit, but some of the things are kind of like a gimbal lock. You can find singular configurations, and those are solely due to scalar parameterization of its configuration space. So if you just describe your system directly on the manifold, you can't get into issues such as that. So it allows you to build kind of a more succinct control architecture that doesn't have to include all these catch cases. This is kind of more of a intuition-based comment, but I think that as you want to do things that are more complex, build really high degree of freedom robots and have them actually do very sophisticated things, I think it's smart to kind of keep a compact notion of your dynamical equations. So thank you.
In the red jacket over there? I've got the mic.
Yep.
Okay, so I've actually written one of these kinds of symbolic equation packages before.
Okay.
And the issue of whether or not you want to do this directly on rotation matrices is generally not, or I should say that decision is generally not one that people have taken. Usually they use Euler parameters, where presumably you would have less drift because you've only got one kind of degree of freedom in the going off of the kind of rotational constraint manifold, rather than 6 additional ones. Okay. And I think, so actually I've got 2 kind of questions, and I think they're both related. One is I don't see...
You only have time for one.
Okay, so I don't see why you can't simulate with those equations of motion, and if you're able to simulate, then you should be able to check the drift from the constraints and compare against other existing packages. Thank you.
Yeah, thanks. That's a great question. So I believe that the equations in the top right for the quadrator are in a simulatable form. So yes, we can compare them to drift cases for an Euler angle parameterization. And I think that would be a great comparison to make. We haven't done that. Or, go ahead.
Euler parameter, not Euler angle.
Okay, thank you.
Uniquaternion.
Okay, right. I agree that that would be a good comparison to do. The equations in the top left, for example, those are not in a simulatable form because there's these extra degrees of freedom packed into each unit vector. So to get it in kind of a state space representation, you have to cast it as a different computation.
Hey, Brian, he's going to set up.